ACVIP Perspective on Safety Analysis using AADL. The previous video, ACVIP Perspective on Safety Analysis using AADL, illustrated the basic ideas behind the architecture-centric virtual integration process, ACVIP, using a small model of a control system. AADL modeling eliminates component integration concerns, evaluates alternatives, automates validation and verification, and iterates that process from conceptual to detailed model design. This video will expand the control system model and focus on the system's design for handling errors. System engineers should account for component and system errors like physical device failure, communication and network errors, or a system breach. AADL analyses are rigorous and comprehensive reliability and safety design evaluations. Model-based analysis helps identify architecture-induced, unhandled, testable, and untestable faults, and understand root causes, contributing factors, impact, and potential mitigation options. This video will showcase error annex and safety analysis. This presentation was developed with two viewpoints in mind: model creators and model users. Model creators are responsible for providing a sufficient amount of information to describe the proposed system and support further AADL analysis. Model creators will specify data processing and transmission, communication transfer mechanisms, as well as system architecture to outline how the data is handled. When the model is ready, model users can review analysis provided by AADL to check for errors and inconsistencies in current design, and to verify that the current model meets the requirements and produces sufficient results. The previous video focused on how multiple iterations of model development and analysis are critical for ACVIP process. Expanding to error handling and safety analysis in this video, let's apply the same mindset and methodology when we describe how the system handles errors and which safety goals we need to achieve. Like we've seen before, there are multiple stages in the project with separate steps to consider. In the beginning of the project, during acquisition, model creator should identify the errors that can occur in the system, decide how they will be handled, and add an error annex to the system model. It is important to specify enough details to support the conclusions reached in safety analysis. As we go through the cycle of refining the design of the system, analysis needs to be run to highlight the spots for improvement. Analysis will provide evidence which can be used to guide decision-making on how to move forward with a better system model. Finally, during product implementation, the evidence from model analysis directs corrections in existing designs and provides a basis for comparisons to previous and future analysis results to determine whether the design is closer to meeting all constraints. Safety analyses are conducted at the system level. They are often conducted very early in development using high-level requirements, or very late in development with more detailed requirements, but with implementations already completed. Safety-critical systems, as used in the automotive, avionics, or aerospace domains, are becoming increasingly software-reliant to the extent that the system cannot function without the software. On one hand, the software system provides an integrated set of functionality to operate the system and manage failure and unsafe conditions. Current safety engineering best practices, such as DO 178B and C or SCE ARP 4761, are labor-intensive and only performed as part of the system engineering process. At the same time, increased interaction complexity of the embedded software with the hardware platform and mechanical system has resulted in the software to be a major source of defects with potentially fatal consequences. To address these issues, the SAE Architecture Analysis and Design Language, AADL standard, has been extended with an error model annex to support architecture fault modeling and automated safety analysis. One of the objectives of the SAE Error Model EMV2 Annex standard, an extension to the SAE Architecture Analysis and Design Language, AADL standard, is to automate safety analysis methods by supporting them through analyzable architecture fault models. It allows the user to annotate system and software architectures expressed in AADL with hazard, fault propagation, failure modes and effects due to failures, as well as compositional fault behavior specifications to facilitate incremental and scalable automated safety analysis. ACVIP methodology guides us to go through multiple cycles of analysis and changes in the model. The advantage of modeling the system early is in getting a more structured representation of the desired outcome compared to early requirements. If AADL models are used, safety analysis can be easily rerun. However, modeling in SysML requires additional steps to change the analysis every time the model is altered to adjust for new model structure. Error model creators use the error ontology provided in AADL to define the flows of erroneous data in the system. Users of the model will implement these structures in the system. In particular, we will illustrate the use of hazard descriptions to support fault tree analysis and others. First, we show the types of error modeling and then apply them. Standards and guidance documents for safety-critical systems outline recommended practices such as functional hazard assessment, FHA, preliminary system safety assessment, PSSA, full system safety assessment, SSA, and common cause failure analysis. Other methods include failure modes and effect analysis, FMEA, and its variant failure mode effects and criticality analysis, fault tree analysis, FTA, availability and reliability prediction via reliability block diagrams and stochastic Petri-net or Markov models, and architectural designs such as using system partitioning as a protection scheme for fault isolation and containment, DO178B and C, and ARINC 653. These methods are labor-intensive and therefore are often applied once in the life of a system. For example, when a development team performs an FHA, they record only hazards that result in catastrophic failure. Later, when performing an FMEA, experts explore failure modes and one or two levels of effects. Due to the large effort involved, trade-offs between alternative designs are often not examined using an FMEA. Consistency between FHA, FMEA, FTA, and other analyses is typically maintained by inspection of documents that capture the results of these analyses, another time-consuming and fallible activity. Alternatively, by generating safety analysis representations, such as fault trees, from AADL models annotated with EMV2, we ensure that architectural changes are consistently propagated and reflected in analysis reports when repeated. This approach maintains consistency across analyses beyond safety to include performance, security, and other objectives. The content of the AADL error model directly supports many of the architecture analyses that we will apply. These early analyses address the earliest parts of fault, error, and failure. FHA, Fault Hazard Assessment Analysis, focuses on what could go wrong in the system. Analysis collects the reference types from the error annex in each component and presents them in the table. The error annex has reference type hazard, which portrays how expensive this error is to the system. FTA, fault tree analysis, calculates probability of events occurring. Error propagation is represented as a tree, and analysis trickles down from the main root of the system to all possible paths of errors. Each leaf shows a probability of the error occurring, so you can see how likely it is to go down through all levels of the tree. In the model, probabilities are specified in the Annex section. Analysis also combines probabilities on each level of the tree. FMEA, Failure Mode Effect Analysis, traces the effect of an error happening in a component. For example, error turns off the light. What are the ramifications of light being off? Think about a fire in an airplane and the system ignoring the error. Following implications, what does it mean to the health of the system? The Error Annex, EMV2, in AADL defines constructs with two different scopes: component scope and composite scope. Component scope means that errors that occur can be handled and eliminated within the unit, and no other component needs to be aware. In our example code on the right, we see that if BCSU subsystem detects no power, the component will transition from operational to failed state, and no value will be propagated out to the other components. Composite scope means that errors are propagated into different components. For example, the error will propagate out of one of the interface ports to all of those components receiving output from that port. In our code on the right, we can see that if either monitor or command process fails, the BSCU subsystem changes its state to failed. This means that subsystem error state depends on a composition of component error models. The objective of these error models is to represent possible errors and design control flaws which handle those errors as close to the error source as possible. So what is an error? An error is an incorrectness that results from executing a fault and perhaps will cause a failure. In our example code, we'll use no power as an error. Let's review other basic error model concepts. Error type is a classification of errors. In our example code, we are using predefined types from error library. However, error model is extensible, and you can derive new error types that fit your domain more closely. Error propagation defines the error flows from one element to another. This is better illustrated in a composite error model scenario, where perhaps one component incurred an error and passed the control over to a different component to handle it. Flow will define the direction that the error will follow from one component to another. Error source defines the location of the fault that produces an error. The command system is a part of the BSCU subsystem from the previous slide. In the code example on the right, break is an error source in the command component. Error sync is the location at which the error is handled. The command system produces data from the break pedal value. This component is an error sync for the error side and may fail from power-related error and service-related error. In this case, no pedal. In the previous video, we showed how nominal behavior of the element is defined. However, defining an error behavior of the element is equally important in system design to show how and where faults are handled. These slides present component and composite error models. Component error models focus on action inside of a single component. There are 3 different ways that errors can be defined in the component. The component may be a source of the error, in which case, error flow should be defined from the location of the fault that causes the erroneous execution. The component may be a sink of the error, or the error may pass through the component. See examples on the bottom right picture where no data message is passed on from component P1 to component P3. A composite error model focuses on how components communicate with each other. In the picture below, we see that component A passes the late data error from P2 port to component B's P3 port that receives it as bad data. At the early stage of development, the model is more abstract. The model creator composes a set of components, including both nominal and error models. The model user can follow nominal flows and trace the corresponding error flows using error paths and nominal connections. As the models evolve, both nominal and error sources, sinks, and paths are assigned types. Flows across components are checked for compatibility. The error model Annex provides a set of available error types to choose from, but error model is extensible, so you can derive new error types that more closely fit your domain. The composite error model captures the propagation interactions of 2 or more components. The state of the composition is defined in terms of the error states of the composed components. The SCS is a composition of the sensor, controller, and actuator. Its very simple error behavior is represented below. As you can see, if either one or multiple components like simple sensor 2, simple actuator, or simple controller fail, then the whole SCS system state is set to fail stop. We continue to use the example from our previous video by adding a model of the error behavior of each component. This will enable the application of several standard analyses such as functional hazard assessment, fault impact analysis, and others. The AADL models have less detail than later models, but sufficient detail to compute the relationships needed to support reasoning. The model of the hazards that may be present in the running system are the basis for much of this analysis. Our simple control system model right now has only 3 components: sensor, controller, and actuator, with assigned nominal behavior. The constructs used here will focus on error modeling. Some features have been omitted for pedagogical purposes. Let's look back at the sensor component from the last video. The definition of an element is divided into 2 parts: specification and implementation. The definition of sensor used here shows the sensor as the source of sensor data. Outports and bus accesses allow this data to flow to the other architectural elements. The property values given in the implementation section specify how the flows behave. In addition to being a source of sensor data, The sensor might also be the source of error. For example, if the sensor is expected to produce data at a specific rate, if that data is not produced, that is an error. It is an error of emission. The program logic needed to handle that issue is different from the flow for nominal data. The Error Model version 2, or EMV2, provides the capability to model those conditions, including a taxonomy of types of errors. Below is one of 4 families of error types available. Let's look at how Error Annex is represented in AADL with Component Error Model. Highlighted are 3 different sections of the Annex, each with its own purpose. The red section is defining error types by names. You can define your own error type or import from Error Library. In this example, we are using fail-stop behavior from Error Library. The yellow section shows propagation, what leaves the component. Imports and outports allow data to flow through them, go through in and outports. For example, value and service emission errors are propagated through data out outport. Since the component can produce an error, flow F2 is designated as a source of service emission and value error for this component, and will later help to pass the error information to the appropriate part of the system. The green section shows how things behave, what events can occur, transitions between states because of these events. We defined 2 error events, service emission and value error event, that will be propagated through flow F2. Once the error event occurs, there will be a transition from operational state to fail-stop. We just used fail-stop behavior from Error Library in the previous slide, but let's look at how fail-stop behavior is defined. There's one error event named failure. Just below are 2 state definitions, initial operational state and fail-stop state. Error behavior also lists a transition from operation state to fail-stop once failure error event occurs. This is just a simple example. Error Library contains more error type definitions and reusable state machines of interacting error states. The model creator composes components, including the error models. The model user can follow nominal flows and trace the corresponding error flows using error paths and nominal connections. Switching to a more complex example, Composite Error Model. The Composite Error Model captures the propagation interactions of 2 or more components. The state of the composition is defined in terms of the error states of the composed components. The SCS is a composition of the sensor, controller, and actuator. Its very simple error behavior is represented below. Here, failure of sensor, actuator, or controller results in system fail-stop. An error not handled within a component flows to a connected component. Those flows occur through ports defined in the specification. These propagations participate in error flows. This portion of the error model defines a state machine for sequencing error behavior. In particular, moving from one state to another is defined in this machine. At this time, there is no link between the mode defined in the core and the error machine in the error model. We will use a portion of our symbol control system, SCS, model. The constructs used here focus on system runtime behavior. Some features have been omitted for pedagogical purposes. Symbol control system model consists of 3 main elements: sensor, controller, and brake actuator. Lines between main components represent connections that control data flow, such as exchange messages or remote call RPC. Buses provide a data exchange mechanism between components. In a real-life scenario, different vendors might need to be utilized to purchase each component. Even though vendors often list the specifications of their products and available communication methods for a purchased part, the system engineer is still responsible for putting all pieces together and making sure that components can communicate with each other. It is important to note that this is one of the areas that introduces a lot of errors, which is why using ACVIP methodology along with AADL analysis is so critical. It virtually integrates multiple components that you wouldn't see working together normally before implementation. AADL analysis can help identify errors in device communication that otherwise would be missed. Getting back into ACVIP methodology mindset, we would want to get more familiar with the cycle of changing a model and running analysis until all of the requirements are fulfilled and no issues are identified by AADL analysis. As we get later in project development, things will be more precise. but predictable analysis provides early guidance for decision-making. Model Creator must run analysis on different types of attributes if any changes are introduced to ensure that modularity stays within acceptable bounds. With predictable analysis, we are interested in analysis of different types of attributes, not just latency, not just safety or security, but all of those. For example, a model user might look at the initial fault tree analysis and see that it doesn't meet the system stability requirements. The model creator will decide to improve the system components and make trade-offs. However, analysis should be run again to verify that modularity stays within acceptable bounds, and other areas like safety or security are not negatively affected. FHA, or Fault Hazard Assessment Analysis, focuses on what could go wrong in the system. The analysis collects the reference types from the error annex in each component and presents them in the table. As we can see, FHA analysis provides a list of failures with indication of their severity and a likelihood of hazard occurring. Since FHA analysis collects the reference types from error annex, the model should use reference type hazard, which portrays how expensive this error is to the system, and define properties that will be later used in analysis. FMEA, Failure Mode Effect Analysis, traces the effect of an error happening in a component. For example, error turns off the light. What are the ramifications of light being off? Think about a fire in an airplane and the system ignoring the error. Following implications, what does it mean to the health of the system? In the model representation, fault impact analysis looks for error propagations and flows to track how the error is spreading through the system. FTA, fault tree analysis, calculates the probability of events occurring. Error propagation is represented as a tree, and analysis trickles down from the main root of the system to all possible paths of errors. Each leaf shows a probability of the error occurring, so you can see how likely it is to go down through all levels of the tree. In the model, probabilities are specified in Annex section. Analysis also combines probabilities on each level of the tree. The presented model establishes the hierarchy of errors between different components. The probability of each error should be specified in Annex section. It is important to think about error handling, especially in safety-critical systems. ACVIP perspective can be applied to AADL error models before implementation has started, and methodology encourages us to go through multiple cycles of analysis and error model changes. AADL provides a variety of predefined error types and analysis. However, the error model is extensible, and you can derive new error types that more closely fit your domain. Achieving ACVIP methodology without AADL is possible. However, it introduces multiple complications. With SysML, each user needs to write their own analysis, and there's no way to validate those who are outside of the organization. With AADL, analysis comes pre-built, so it could be easily shared between contractors. If the model changes, SysML analysis will need to be rewritten to adjust for a new model structure. However, AADL analyses are robust enough to handle model changes and do not require any additional work to run. It is important to remember that the fidelity of the analysis is determined by the details in the AADL model.